Hello everyone. In today's video, I'm going to share with you how to use prime factorization to solve questions involving perfects cubed and cube root. In my previous video, I shared with you questions involving perfect squares and square roots. So today I'm going to share on perfect cube and cube root. Okay, now perfect cubed actually have a similar idea as volume of a cube. Okay, so we know that volume is of a cube. A cube has all equal sides. So a volume is involving three dimensions, length, breadth, and height. So if we have a cube of side 2 cm, then we'll have 2 times 2 times 2, that gives us 8. Length is 2, breadth is 2, height is 2, so the volume is 8. And 8 is a perfect cube. Let's continue to list. If the cube has a side of 3 cm, then the volume will be 27. And 27 is a perfect cube. Okay, so let's move on to a 10 cm cube. Then the volume will be 1000. Alright, so the circled numbers are called perfect cube, or some books will call it the cube number. Now the reverse will happen. Alright, when we talk about cube root, it is the opposite. So the opposite is when we have the volume and we want to find the length of each side of a cube. So it will have to get from here. So the length will be cube root with a 3 there. Cube root of 8 gives us 2. Cube root of 27 gives us 3. And cube root of 1000 gives us 10. Okay, all right, so that's a very simple illustration of what is a cube, what is a perfect cube, and what is the cube root of a number. Let's take a look at this particular question. Express 132 as a product of prime factors, giving your answer in index notation. This one is okay, quite easy. Then part B, the number 132n is a perfect cube. Find the smallest possible integer of n. Let's take a look at question A. To express 132 as a product of its prime factors, we will definitely do it using repeated division. Now, and since 2 is an even number, we will start off with the smallest prime number, which is a 2. Okay, so we get 66 here. Moving on, we can still divide it by 2 to get 33. 33 is an odd number, so we have no choice but to move up to the next prime number, which is number 3, and that gives us 11, and 11 is a prime number, 11. All right, we stop at 1 when the quotient is a 1. So over here we can see very clearly that 132 is 2 times 2 times 3 times 11, meaning it is 2 square times 3 times 11. So A is completed. Right, now let's look at B. B is not difficult. B is an extension of A. So if I have a number that is 132n, it's an algebraic expression and it is a perfect cube. Alright, so meaning 132 times n, that means 2 square times 3 times 11 times n is a perfect cube. I'm going to rewrite this algebraic index notation. by expanding it, then it becomes something that is more visible. Now, what should the value of n be so that 132, which is represented by 2 times 2 times 3 times 11, this is 132. After multiplying n, it should give us a perfect cube. So a perfect cube means it must be a set of 3. So let's take a quick look. Now, over here, we only have a set of insufficient. So we need one more. So we need like this. Okay, so it must be a set of 3. Next, this one over here, we have only one number 3. So we need 2 more. Then we get a set of 3. Over here, we also need 2 more. Then we get a set of 3. Okay, so what have we added? What are the prime factors that we have added into that algebraic expression? We have added 1, 2. We have added 2 3s. And we have added 2 11s. So the numbers that I've circled, 2, 2, 3 times 3, 11 times 11, actually they all come from the value of n. So what is n? What is n actually? Okay, so I'm going to use this part here. So n is actually derived in this manner. So let me rewrite. This is the question. Okay, it's actually 2 squared times 3 times 11 times n. And what is n? N is actually the numbers we have circled. 2, 3 by 3, and 11 by 11. So this whole thing is n. This is what we have added to that algebraic equation. So the value of n is in fact very abstract. Okay, so I'm going to rewrite the one that I boxed up in blue using number notation, okay, index notation. So this is the one that I'm talking about. Okay, so this one can be rewritten as this. 2, n is equals to 2 times 3 square times 11 square. And it has a very big value of 2,178. So this is the answer for part B. So part B, the answer is this. Okay, right? So it's just an extension of what we learned in the previous video on perfect square. Do play back this video to understand how to go about doing this question 1B. Okay, now in my next question, I will first illustrate how to go about using prime factorization to answer questions involving perfect cube. Let's take a look at the question. A, written as a product of its prime factors, we have 1400, and 1400 is equal to 2 to the power of 3 or 2 cubed times 5 to the power of 2 or 5 square times 7. Okay, so 1400 in index notation is 2 cubed times 5 square times 7. Now, we are given this algebraic expression. So, and they told us that it is a cube number. So what should this integer k be? Alright, okay, so what is the smallest value of k? Alright, okay, so I'm going to use the next slide to go through this. So, continue. Let me rewrite this expression given to us. 1400 is 2 cubed times 5 squared times 7. I'm expanding this, so 2 times 2 times 2 times 5 times 5 times 7. So this is 1400. And we are told that the perfect square, the perfect cube is 1400 divided by k, meaning 2 times 2 times 2 times 5 times 5 times 7. The whole product is divided by k, and it will end up to be a perfect cube. Now, if you remember in our previous slide, perfect cube must be a set of 3. Let's take a look at the numerator. In the numerator, we have this set of 3, which is very good. Unfortunately, we don't, this log over here, the one that I circled in purple, this is no good. This one can't give us a set. Okay? The one that is in green is excellent. It's already a set of 3. It's already 2 cube, which is what we want, perfect cube. Okay, so the one that is in purple, 5 times 5 times 7, is impossible for us to get a perfect cube. So what we need to do is we just need to remove the one that is in purple. Remove. How to remove? By dividing away 5 times 5 times 7. Okay, so that means 5 times 5 times 7 must be k. It has to be k. Okay, all right. So k is actually 5 times 5 times 7. Okay, so 5 times 5 times 7 is actually 175. So it is done, part A. Right, so once we take 1400 divided by 175, we will get a perfect cube. Okay, we need to get rid of the one that is in purple, and we just retain the one that is in green. All right, okay, let's move on to part B in the next slide. Now, we are given this expression 3m times 5n times 7 cubed, and they told us that it must be a multiple of 21. So they asked us to find what is the value of m and n. And m and n are integer values. Okay, to be a multiple of 21, we have to do repeated division. Okay, so let's do with a 3 first. Oh, simple. All right, 21 is merely 3 times 7. 21 is a very simple equation making up of two prime numbers, 3 and 7. Okay, now that means this expression over here, all right, 3m plus 5n, sorry, 3m times 5n times 7 cubed should contain 21 in it. And 21 is equal to 3 times 7. Okay, we have a 3 here, we have a 7 here. We only need 1 3, we only need 1 7. Okay, all right. So what is the value of m now? Since we only need 1 3, then m has to be a 1. Why is that so? This is the reason. Because 3m means 3 times 1, and that is 3. So we only have one digit 3. Okay? Alright? Now, this 7 cube, okay, is actually 7 times 7 times 7. 7 appear 3 times. And we only need one number 7, which is this one. Fine, because it has to be a multiple of 21, so it's okay as long as we have one digit 7 there. So this is okay, retain. Now the headache is here. What about 5n? We don't need a 5 because in this, we don't have a 5. There is no prime number 5 in 21. So we are not interested in a 5. So what do? We have to multiply it by a 0 so that it becomes a 0. So the 5n term will be a 0 in value. So to do so, n must be 1. N must be 0. So when n is 0, 5n becomes 0. Then our expression would be, this expression here would become this. Okay, let me rewrite. The expression in green would be 3, because m is 1, right? So it's just 3. And 5n is 0, right? So it becomes like that. So this particular number is definitely a multiple of 21 because in that 3 times 7 cubed, it contains 21. Okay, so from here we can conclude that n is 0 and m is 1. So this is our answer for part B. So we have already found the algebraic value. The unknown n is 0 in value. The unknown m is 1 in value. So when you substitute m and n, 1 and 0 respectively, into the expression 3m times 5n times 7 cubed, the new number is indeed a multiple of 21. Okay, we have completed discussing this question or questions involving prime factorization to solve questions on perfect cube and cube root. In my next video, I will be sharing with you questions from the GCE past year's papers. Alright, and this time I will combine both perfect square and perfect cube. To know when I will be uploading my YouTube videos for questions involving GCE papers, remember to subscribe, then you will be notified. Okay? Now, if you like my today's sharing, give my video a thumbs up, a like, drop me some comments, okay? And do share with friends. Thank you for viewing my video. Thank you for supporting my channel. I really hope my explanation is clear to you. Thank you for your support. In the meantime, do take care and stay safe. This is Joseph signing off. Goodbye.